a little bit of a theory. I hope you agree that what we've been doing so far is more of a method. If you think about it, I did a little bit of a theory. I'm going to summarize it here. Is more of a method, right? How to actually get this thing done. So here's a summary. What was the very beginning of this chapter? How did I start? There's a vector space V there, and this U1 plus the direct sum of U1 and UM that we looked at in the very early part of the semester. But what was the additional condition we're having here? U1 being invariant, right? Invariant. If you hit it with a T, it doesn't go anywhere. They stay inside the U1. If you think about it, that's the right notion of decomposing the map. It's not mingled to each other. What is the one extra thing? Indecomposable property, right? Is indecomposable right there. So that was our goal. If you have a vector space and we have a linear transformation T is given, we wanted to accomplish this. Break down to direct sum. Each of them is invariant and indecomposable. And make sure when we say indecomposable subspace, it means is invariant in the first place. So I'm not going to say that anymore. All right? So if you have enough eigenvalues, this will be all one-dimensional indecomposable subspaces. Does that make sense? One-dimensional. If not, then it's a Jordan form. That's the best you can do. So here's an example of Jordan form. And if you have one eigenvalue, then you can pull it back. That was the chain we looked at. And consider the subspace under that chain. You can even take a shorter chain, but we have a tendency to go as far as you can. And with this thing, that was one of the theory we did. These are linearly independent. Okay, if you put the linear coefficient, you can push it back to show that. And therefore, you can consider coordinate matrix. Under this chain, the coordinate matrix becomes this Jordan form. Okay, that's why we're doing this Jordan form. If somebody asks you, down there in the street, grabs you and asks you, why are we doing the Jordan form? And what's your line of the answer? Because we wanted to decompose a vector space down to indecomposable subspaces. How do we do that? The chain, the Jordan form, is a way to do that. Okay? So let's not forget this big idea, not just how to do it. Never forget the why we're doing this. And this is a wonderful decomposition, and we want that. Because maps are getting down to a smaller dimension and easier to understand. There's one other thing in the mathematics. If you look at a complicated object, in a reasonable way, you decompose it into a few smaller objects, you understand it better and control it better. Like numbers and prime numbers, that's one thing. Okay? All right. And second item was something we're going to look at today. We have this eigenvectors, eigenvalues lambda k. Not necessarily they're different, but for each we have these linearly independent eigenvectors. Maybe lambda 1, lambda 2 is the same. Then it's lambda 1, v1, v1, and v1, v2, v1, v2, 1. They are linearly independent, but for the same eigenvalue. Things like that. Whenever you have it, you have this eigenvector. So each of them you have this chain, right? This index gets crazy, but that's the only way to deal with it. Each of the linearly independent eigenvectors, you have this chain, and you consider this chain, right? Just like we did with this one example. And they, in itself, it becomes an invariant space, correct? It's an that's one of the things we proved, why it's an invariant. So if you look at the invariant space, the T, if you hit a T, it stays in there. What is the matrix? Matrix looks exactly like Jordan block. Right? Here is the one of the chain. How does the coordinate matrix look like? It's Jordan block. Each of the eigenvector, if you consider the chain, they gives you the Jordan block. All right. So if these are linearly independent eigenvector in the first place, we have this bunch of different ones, right? W1 to Wm. Here's a new theory. They're actually all direct sum to each other. It's one of the theory that we use. Before, we looked at only individual one and understood this chain is actually linearly independent. I'm asking more. Doesn't matter if it is all eigenvectors of the same eigenvalue, they're still linearly independent. Okay, so if you have multiple chains, as long as your bottom vectors are linearly independent, they're all linearly independent, therefore forming a direct sum. Okay, does the statement make sense at least? Any question about statement? Each of them coming with a chain, right? As long as the bottom of the chain is linearly independent, this entire thing that is involved in this chain, the multiple chains, they're all linearly independent. That's what it says here. They're direct sum. Okay, make sense? Yeah. So if I draw a picture, let me abbreviate it with just V1 in here. There is this thing in the chain, right? And V2, that's eigenvector. There's another chain. Maybe they are eigenvectors for same eigenvalues. And then we have the bunch of them. This thing is linearly independent. We proved that earlier. But in the new statement is that all these things, now we have multiple of them, they're all linearly independent. That's what this statement is. Right, the minimal operator, very first time when we exposed the minimal operator, it went like this. You looked at the matrix, right, of a Jordan form, and then we were able to see that minimal operator must be this. So it's a slightly different approach where we were exposed like this. We have a basis V1 through Vn. In your example in homework, it was E1 through En, right? But it's not necessarily the column vector matrix. It's just an abstract vector, V1 through Vn. And you go through V1. Remember how I get this PKT? That was like, you start with a V1. Next one is a TV1, right? And T squared V1. By keep doing that, we have a linear relation on that each of the V1, V2, Vk. So we have operators there. And least common multiple of each operator for each of the base member was actually the minimal operator. We saw that in that homework problem. So the minimal operator is now computed without using the matrix or anything, just augmented matrix a couple of times. You can see this minimal operator kicking in. So it's best to write this minimal operator for distinct eigenvalues into a typical factored form of a polynomial. It's like this. All right? I think we understand this much in here. This is what we've been doing with the examples in recent homework. Does that make sense? This is a new theory which, if we have time at the end of the semester, we will cover it. But what happens with the minimal operator is a wonderful thing happens. This V is now finally decomposed. This reveals the shape of decomposition in here. Null space of this one, which is written here. Null space of that one, which is written there. And they're all direct sum, and that makes entire V. So this is wonderful, wonderful, wonderful part. If you have a minimal operator, if it is factored like this, and null space of each factor really gives you the direct sum of V. Okay? So this will have from here, you just focus on analyzing this guy. Multiple Jordan blocks kicking in. All right. So this allows you to conclude, basically, every linear operator T has a Jordan Jordan canonical form presentation because of this theory. All right, we can't do all of that in here, but we might eventually. Does that make sense? Great. So with that, we can proceed to the next line. If V with a scalar field, a complex number, then V is decomposed into all the Jordan block representation. These U1 and UM is just simply one chain, right? Each of them, U1 and U through UM, is one of the chains, and another chain. Each of them has a Jordan block representation. So that's the final theory. using this one, each of the vector space is decomposed into the direct sum of the Jordan chain. That's what I eventually called, and each of them has this Jordan block representation. Knowing that, we can sometimes quickly calculate without checking everything. And I said earlier that these subspaces involved is not unique. Remember, if the simplest case, let's say the V is actually span of two eigenvector V1 and V2, right? And that would be U1 and U2, because each of the eigenvector will generate eigenspaces, right? And they are actually invariant, because eigenvector is going back to itself, and it's a dimension 1, so it's indecomposable. But it's not unique. You can choose a different basis here. Remember W1, you can choose a different basis, and it's going to be different subspaces. That space itself is not unique. But what is unique is this Jordan block. However you found this chain, the shape of the Jordan block never changes. It's kind of a matter of rearranging it. So there is a uniqueness in terms of shapes of the Jordan block. However you do it, you all end up with exactly the same shape of a Jordan block. It's a matter of the blocks are kind of swapped around. All right? And second part is that if you look at each of them, it's a Jordan block. You know how to calculate. It's not here. What is the minimal operator of this one? It's a Jordan block in here. The full dimension, right? The minimal operator of this one is a t minus lambda I, whatever the size here, I'm going to call L. Then you have to go all the way up to L, right? This is the minimal operator. What is that L? Is a dimension of this block size, and down there, each of them is a one chain, and this entire dimension is the correct block size. So if you look at each of a Jordan chain, that's not a standard term, then the minimal operator is going to be this one with the correct dimension in there. But they're not necessarily associated with the distinct eigenvectors, so you have to still consider LCM. These can be all same eigenvector and different chain. I mean eigenspace, same eigenvalue. That's what I mean by that. So that's kind of the result that is reformulated or readily available so far what we have discussed. Okay? Does it help you to summarize what we have discussed so far? Very nice. So I'm going to go to next part. So I don't know my experience, and if you just throw this heavily theoretical structure, it's not real to the students. Once you see many examples and you understand theory better. So here's the final picture of how to compute the Jordan form. I struggled, and you struggle sometimes to compute that chain, right? So here's how you compute the Jordan form. So you need to understand this one to do the homework. I'm not going to really give you the concrete example of doing this one. You have to understand. At this stage, I believe you will be able to understand. All right. I'm going to give you the eigenvalues. So compute eigenvalue, first stage. This is not necessarily matrix. This could be a finite dimensional abstract vector space, right? If it is not a matrix form, how would you find these eigenvalues? Do you know how to? If it is just given theoretically, what would be the theoretical procedure that you go about to compute the eigenvalues? I want you to look at number 3. Item number 3. That discovery of the minimal operator does not use any matrix, right? It's just that, and you have a minimal operators there, right? And from what we argued in the homework number 6, that these coefficient, as you factor those, supposed to be eigenvalues, right? So you just row reduce it, figure out the minimal operator, factor it over complex numbers, then those coefficients are eigenvalues. So this makes sense. Theoretically approaching it makes sense. The next part is that for each of the eigenvalue, compute, I already showed you the theoretical part, compute of a null space of this type, right? Lambda k I. What would that compute if I just put like this? Lambda k I. That's the same as eigenvectors, right? This will be the eigenvectors. The dimension of this one will be the dimension of the eigenspace lambda k, right? Does that make sense? Anything that goes 0 is an eigenvector. Now we think about the chain, right? Chain, all that thing is put together as you raise this power. It's coming from a higher and higher level. So you go all the way up to the maximal. LK is maximal. Is this maximal part make sense? Because it's finite dimensional. As you go and higher, it picks up more and more vector, but it should end. Right? It should end. It will stop eventually. But how do you find this maximal? Number 3, the minimal operator tells you where to go. That the coefficient is the maximal. But in practice, you can just hit a couple times an enter key in the Mathematica, and you see that it doesn't pick up any more vectors anymore. And you know that ends somewhere. In practice, does that make sense? You solve this one. In Mathematica, the command is null space. So how are you doing with the Mathematica? Are you ever using it? Did you use Wolfram Cloud or Wolfram Alpha? This one could be a lot of typing work. If you use Wolfram Alpha, Wolfram Cloud is better. It's online. You can just type, copy and paste, shift enter. It's going to execute it by changing some numbers. All right? If you have any questions, let me know. Or however you do it, you just copy and paste into your calculator. If you're good with that, do it, however you do it, more efficient way. But there are many vectors here, 10 vectors to deal with it. And it's necessary to fully understand the structure. You have to hit high dimension. Sorry about that. Okay? So maximum power, understand? You change the number until you realize it. Hey, dimension 5, next level, dimension 5 again, it doesn't pick up any more vectors. The following part is theoretically very simple. In practice, it's very difficult. But you have all the tools, actually very basic tool, to overcome this problem, which I will leave it as an exercise. Hence, it's going to be an advanced problem. But it's not really advanced. So here's a VK. That's entire null space is now understood like this. VK represent the null space of this one. All right? We wanted to strip this one off a little bit more. We're going to compare this one with one lower level. I hope you see what I'm doing is actually pulling it back procedure that we were doing and all at once, not just playing with one vector. So this is going to be one lower. This is not index, it's actually one lower power in there. So how would you compare that? There will be more vectors potentially there, right? Anything that is killed here will be killed here. If it is killed already in LK minus 1, it'll be killed in LK power. Potentially that has more. Because it's the maximal, it actually has more vectors. More vectors than in here. How would you best describe that? It's not union. What is the operation to best separate additional things in a vector space? Direct sum, thank you. It's a direct sum. There must be some vectors out there. It's a direct sum, right? So I'm going to call that one VK LK. We're going to strip off one at a time all the way down to the V1. So it's going to be length is going to be LK. So the highest level is LK. We want a chain, right? We want a chain. So best way to create a chain is that just push this one forward in here. That naturally creates chain. Maybe I have 3 independent vectors here, right? You push it downward, down to level. So here is the next level you need to understand. What are we going to do about this guy? We go down one more level, right? LK minus 2. It's all theoretically easy to understand. This one will have whatever it's outside, right? With the direct sum, there's an optimal choice of vk of lk minus 1. Does that make sense? There will be some choice that completes these two parts in here. But there was vk, lk anyway. So let me write that here. Here's vk, lk. Right? So when you push this one by one product in here, t minus lambda ki. That makes perfect sense. If this one is, if you go all the way to lk, it dies. If you do one more times, and it's going to die in here. Right? I hope that makes sense. This one, if you push one more time, and it's supposed to be in here, because, hope that makes sense. One copy of t minus lambda k. If you do lk minus one more, that gives you the full copy. So if you push it with this one, it lands it in here. But it doesn't guarantee that it's going to land exactly your choice of direct sum. Direct sum decomposition is not unique. Remember that part? So you can choose anything different. You can actually avoid when it lands in. But we want to land it in here, right? So you actually push that one in here. If that has 3 vectors in that, you're going to have exactly 3 vectors in that. Nothing dies. Because anything dies in here is a kernel of all the way down to one level, and these guys are all away from the kernel. So you will verify that. You don't have to prove it. All 3 of them goes exactly go to the 3 vectors, all linearly independent. And you know the dimension of this one by keep calculating with the Mathematica. So you have 3 of them. Maybe this is supposed to be degree dimension 4. Then you have to go and fish out, get one more vectors in there that extends the 3 that is coming from the higher level. Right? We get 3 vectors here from the upper level. If you know the dimension is 4, you got to go and find one more. These are all theoretically easy to say that there exists one, there exists out there one. You actually finding it is some work that you have to go through. Keep using this null space and some ideas. Okay? So all 3 of them in here injectively go into the next level and you extend it. That's how we choose this basis. And you do it again. If you have 4 of them, they're going to injectively go into that, right? To the next strip off and go in like that. So eventually you create vector like this is a vk1, vk2, all the way up to vk lk minus 1 vk lk. In such a way, if you hit it with a t minus lambda ki, this lands exactly in the next component that you cooked up. And if you hit it again, this lands exactly in the next component you cooked up. All injectively, right? Nothing dies and all in here. Okay? So if this has a dimension nk, next one, because it's injective, it has more dimension, right? Potentially. Because it's all injected in there. And here's nk and lk, k minus 1, and so on. So you have a tree of a possibility like this. I started with 3 of them in here. Let me give the tree and that's going to happen. I have 3 vectors, right? You push it all the way to the end. They never dies, never overlap. They all survive. But in the middle of the way, we picked up more vectors in here because there's possibly more. And they developed all the trees in there, maybe somewhere in here. You see the structure? By pushing it, you get these chains. Each of them gives you the Jordan chain, Jordan block. So I'm going to give you necessary tools if you want to do it quickly, but all you need is a null space and a lot of row reduction. Then you can handle this one in a very efficient way. That's our advanced problem. Any question? Is that something that doesn't make sense to you and how to do? Difficult part, the reason it's an advanced problem is how do we actually go out and find out this guy? It is not the union. And if you solve this one, it'll give you 10 vectors, or actually give you 6 vectors, something like that. if you first do it this one. The calculator will give you 6 vectors, and you have to way of figuring out what is these few vectors that is the direct sum with the next level in there. And I claim that you know enough about how to do that. That's the advanced part. All right. I also give you more hints, but I also want you to have a chance to think about this problem. It's getting too long.